which will tell us about proton mass and spin decomposition.
Where do I get that talk here?
You have to close this
I have to close this one. How do I close this one? Okay. That's right here. Okay. This is on the tabletop. I think it's right here. Oh, yeah, sorry. Uploading. Slideshow from beginning. Yeah, right. Okay. Where's the?
Yeah, just in front.
Oh, here. All right. Before I start, I'd like to mention, I'll probably address questions all claim lattice calculations of the initial calculations. I put that in my funding agency also. But I should remind you that there's an American philosopher, Yogi Berra, who would say, well, look, theory and practice are the same in theory, but they're different in practice. That describes our initial. Okay, there are many systematic errors, continuum, the known things, continuum, and even the volume, Carl, and so on. But there's also action. Whether the action has Carl symmetry, not have Carl, that can make some differences in equations, questions, and so on. And then, of course, on top of those, people calculate things. It's not straightforward. You have the inverse problem everywhere. PDF, positive PDF, and also around Tensor. So there are all these issues involved. That's not unique to lattice. This is that global fitting is the same thing. Okay, I'll talk about arc spins and mass decomposition. So the first question is, where does the spin of the proton come from? Well, of course, the quark model answer is very simple. It's all from quarks. And we know that's wrong from almost 30 years now. That the sum of the this experts here, the substitute from the Jaffe, Alice Jaffe sum does not satisfy the experimental bound, and people concluded that the spin is probably total spin maybe 30% or so. Okay, so of course there are many other questions. Where the rest of the spin come from? Why is it so small? Right. One of the reasons is that people at one suggestion is that you look at the anomalous water density, which is field theory, and the suggestion that so maybe the topological term, which is extra compared to the connected insertion part, you can write that as a Chern-Simon term. That in terms of the you put the KB on the other side, and claiming that experimental measurement is actually this one and not the actual current. But that's not correct. This is this operation. This is currents, not gauging current, not such an answer, even the forward matrix. However, okay, so that leaves this is a second hand I heard. So the Proton's thousands paper written on this on the model, and nobody really did very convincing results. That led at least your can, so I heard second hand that Proton speed price is graveyard full. Part of the reason I figure is that because the topological term here is, as I showed, it's very important. That's very local. It's a very local term. It's very hard to catch that in effective theory. To get that effective theory, you need to use additional low energy parameter, trade 1 for 1. It's nothing like a couple like either prime mass and so on. Okay. Now, in the lattice calculation we mentioned, I guess we have heard talks yesterday. They are connected by disconnected insertions, and then you have a group. Okay, that's basically disconnected insertions. To the details. One thing I want to point out is that it would be useful to look at the anomalous water density together with the quark speed calculation. The quark speed calculation people use just active vector current, calculate connected, disconnected. There is a relation. There's something one needs to check out. One thing is that the anomalous water density is this one. Okay, divergence active vector current. And this is the topological charge here. Now, for the first thing you want to do is to make sure that this term in the I don't know what's called a classical or tree level, because you can get this term not through the triangle anomaly. There's another way that Fujikawa showed that you use coming from the Jacobian of the determinant and so on. So I can call that semi-classical whatever term. But this is relation is satisfied in that, for example, if you take overlap fermion, this is satisfied exactly at the true level. So, but frequently people use local current. In that case, you only have one current. In other words, people use the whatever kappa A and so on to normalize to make sure the relation on the on the left hand side satisfies the right hand side. Okay. This thing we think is quite crucial, and we can check out the overlap fermion. Now, on this normalized one, so on top of this, you have renormalization. Okay, and for the renormalization, you have another coefficient here, and then you have a normalization for the mass and the pseudoscalar, and you have a normalization of topological charge operator used, and you can also mix at the true level to the divergence vector. These are convenient. If we use overlap fermion, the reason it's more expensive, probably 20, 30 times more expensive than this one, but we insist on keeping the symmetry. That's one thing we learned from last century. The symmetry dictates a lot of the dynamics. It's very important we keep that. You can see with the overlap, the situation left become much simpler because the Z and ZP cancels out. This realization could be varied, so you don't have to do anything, just take a bare mass. And overlap operator, you can use this one as bare overlap operator, which is trace of overlap operator, is really a definition for topological charge. Otherwise, you use this gradient flow and sure you don't know what this ZQ is. But in this case, ZQ is 1. Okay, there's no modification realization. And on top of this, has been shown by SBU and Tara that the two loop, if you do continuum, the two loop calculation gives you this. This is alpha s squared. And this mixing coefficient gives you exactly the same thing with the same coefficient. So therefore, if you look at the two loop level, they preserve the same formulation. But it's important that one check this relation satisfies, particularly for disconnect insertion, which we did. Now, let's just show you where does this be relation to the quark loop, the disconnect insertions. We can look at the charm and strange. They only come from disconnect insertions. Now here we look at the ratio of the 3-point function to 2-point function, and you sum up all the currents. So the 3-point function, you have a source and sink and current, sum of the current positions between the source and sink. And that turns out is proportional to the separation of the source and sink. In that case, we'll only looking at the slope of this one to get the matrix out. But the topological chart, this function of tau t, you can see is positive. For the charm is negative. They cancel almost exactly. That's why when you calculate axial vector current, you find the charm very small. That's because the cancellation of topological charge and source. And you can show that to people have done that when I have a quark loop, heavy quark loop, and expand it, and that will give me the topological charge with a pseudoscalar current with negative sign up to one of the quark heavy quark expansions. Okay, now for the strange, then this okay, topological charge is the same, but this one getting different. Therefore, that's why they don't cancel exactly. That's where the disconnect insertion comes from. All right, this is good. Now, before I say anything, I should mention a little bit of the technology which we'll use later on. Is what we call the cluster decomposition error reduction. This is frequently seen, particularly when you have a disconnect insertion like eta prime mass. And also the disconnect insertion, glue balls, and so on. You'll find that the correlator falls off. The signal falls off exponentially, but the variance or error goes as a constant. So why is that the case? People just say, well, in this case, then you have a sign problem, then it dies. Okay, there's not much you can do. And you can probably increase the statistics by loading a lot of configurations, but you are only lowering this plateau by power. But this is falling off exponentially. Fighting power by fighting exponential with the power is a typical sign. Okay. And these, for example, the neutron electric dipole moment, the theta term, is also related to this because the volume square root of volume. Okay. Now, this is what we recently realized. People have suspected that may be the case. This is cluster decomposition principle. It used to be known that you have two operators in the field theory, and they should fall off, this exponentially with some correlation length. And so you don't have to worry. For example, if you do experiments, you don't have to worry about anything on the moon. This is very, very far. But the okay, now apply to the operator here for the disconnect insertion. So I have two operators which are separated. When I do the variance, then it's just O1, O1 square dagger and O2, O2 square, right? So this is a vacuum quantum number. When you have vacuum quantum numbers, you can insert a volume, the vacuum. Once you have other things. Once you insert the vacuum, this becomes a product of two independent variances. Therefore, that's why, as we said earlier, as a function of time, it's independent of time. And that's what we saw. That explains that. But also, the thing is, if I do the following, now I notice this is xy and then x r1, r2. If I restrict, because after a certain distance, separation, as I said earlier, it falls off exponentially. After a certain distance, you have no more signal. A normal signal, but you keep on integrating. For example, you do a Fourier transform to get a momentum state, you sum of all the coordinates, and you're accumulating errors with no signal. So that's a very not a very smart way to do it. So you can do it either cut off or using some way to fit it, and so on. I'll show you the results. In that case, you can gain a signal to noise by a square volume signal. Okay, this is the fixed volume by the correlation length of a particular operator you look at it. It's typically Fermi or so. But your box frequently, now we're reaching 5 or 6 Fermi. Eventually, people are talking about 10 Fermi and so on. That's going to grow like crazy. Okay. So the operation is very simple. You can do the or we can do the fast Fourier transform. In that case, the calculation is the V log V. It's very simple. Okay, not a V squared. This is an example. Jane showed us like strangeness in the nucleon. You have a nucleon here, and you have a strange suit. You can look at the this is the operator nucleon interpolation fields. I can look at the relative coordinates between the strange suit and the sig, for example, and I can integrate over the relative coordinates. So I promise that it's to integrate and then eventually to saturate. You don't have any signal anymore, but the error bars start growing. Okay, that's the phenomenon described, and that explains this thing. The variance keep on constant, the signal falls off. So the best way is just cut it off and also fit it. We fit it the constant with the exponential term to get that. This is the same thing for the CT violation in the nucleon. When you look at the face of the nucleon phase, topological charge, it's best to convert the total topological charge into a local ones. Once in local, you can look at the relative coordinates between this, and you can see that this is again flattening off phenomena, which then you can fit. You can see that in a not too large volume, you can get a signal to noise by like 3.6, which is a lot, 10 times the statistic. So calculate. Okay, now here the quark spin that we've calculated so far represents the following 3 lattices, and this lattice spacing is here. It's about 0.085 Fermi. These two are 0.11 Fermi. This is 0.14 Fermi. And last rate is D sub 300 MeV. This is 1 near physical, 170 MeV and so on. We use overlap, and you don't need to know details, but it has power symmetry, like in the Wilson relation, and order A square error is very small. Usually, when you have a power fermions, you automatically don't have order A error, where other fermions you have to tune it and you get only the unshelled relations. Here it's automatic order A square. And overlap, we've tested before, is the smallest of order A among other actions, which will tell you. The certain quantities you can hardly see order A square. Otherwise, you have an extrapolate, and that can be that. Okay. Now, this is one of the GA in the disconnect insertion, and it's our recent work. And you can see that for the light part, UD, and for the strange, you can see that it falls off here, and it's a large distance. And these are the errors. And here we don't gain very much because the volume is not very big. When you have very large volume, then you gain a lot. But here we have not gained a lot. This is only 4.3, 4.5 Fermi. Later on, when we come to 5.5 Fermi, the gain will be much larger. But strange is already a little better because strange is heavier. The correlation length is shorter. We just fit this form to get the results. Now, I want to mention a little bit about non-perturbative renormalization. Okay, we have normalization, as I said, we checked already with overlap fermion. The normalization factor for the connected searching and disconnected searching turns out to be the same. But it cannot be said it's the same thing as other fermions. Clover fermions, one has to check. I don't know how that turns out. Okay. All right. So for the lattice, what we do is here. Okay, we have a U and D and connected and disconnected, disconnected here in a string. So you have five degrees of freedom. And you have a 5 by 5 matrix, which has, I won't go into the detail, this R and mom, which you do the Ri and the mom, and then match that to the MS bar scheme as a scale, and that's what you get. So this is the matching. The matching from MS bar Ri to MS bar requires a two-loop calculations, which is hard. We couldn't find in literature. Well, so we did is to use the topological charge, because topological charge else, as I said earlier in the continuum, it already has an alpha and S. And two loop is the same as the one loop is the same as two loops. We take that calculation from the Ri to MS bar. But you can see that I want to point out when you do the connected to connected, you only have normalizations. Okay, you don't have to take, as I said, U minus. U and D, the connected assertions separately, they only have normalization. They are not mixed from the antipart of the group. Right? So this is something which one hope to be able to extract with the experiments and compare directly connected disconnected exchange. Okay? You can of course recombine them in the conventional form that people do in the singlet, isobactors and octet and singlet. You can do that. It turns out to be exactly the same. The situation is exactly the same. But here you have five quantities which lattice can calculate and experiments can, in principle can measure and should be able to measure. So that is much richer in structure than people conventionally use. Okay. Yeah.
Okay, thank you. So the quantity at the very bottom, the NF times CA dms bar.
Yeah.
Would that correspond to what we normally in the perturbative case know as the
Yes. That's exactly the same thing here. It's just the same coefficient here. It's just that lumped in the.
Okay. Is it any way useful at all to have perturbative information on that quantity? I mean, this has been.
For the quark speed, it's really not that important. Non-perturbative, like the two, it's only 2%, 3%. It's even smaller than the system error.
Okay.
But what can do with the non-perturbative?
No, I understand. I mean, because I think it's now known to for loops even.
Okay, good. If you have a full loops for the Ri and then MS bar, then it means the full loop to do from Ri to MS bar. We could do the non-perturbative Ri. You have full loop, that'll be better. Yeah, sure. Yeah, let me know. We can probably use that.
Maybe I'm not sure whether they're talking about the past.
But still, theoretically, that's important.
I say a few words about that.
Right. In other cases, you have one loop and stuff. But this quantity, even 2 or 3%, if you want to eventually coming down to positions, if this is one quantity, we can control it, why not? Okay, good. All right, sure. Now this is something which uses the disconnected assertion. Is this for the light? Yeah.
Question. So you go back to one slide. Right? There is something that you said that I'm still not understanding.
I'm sorry.
There is one thing that you said that I'm still not understanding.
Yes.
Get from experiments this connected part. I don't see how that is.
I'll show you how possible. We have written several papers on it.
But is it being shown?
Yes, I have papers which we can discuss that, how to separate out the connected and disconnected.
I mean, is this an accepted reality right now?
Oh, well, I hope that, I'll hope to be able to, we can discuss that as a, I cannot just answer here. But we did that for the Godfrey summer violation, U bar minus D bar. That U bar, D bar is in the connected, not the disconnected. Otherwise, U bar and D bar will be the same. But they have a different small x behavior, which one can explore. And also one can use the lattice to somehow extract that. We can discuss that in court. We'll have to read several papers.
That, just to make it clear.
Yeah.
So there are flavor symmetries, right? It was like D3, D8, and so on and so forth. And so how does your, I mean, that's asymmetry.
You can't.
How do you
You can't. That's what. I said, you can do that in a conventional way, SU3, cosmic representation. What I'm saying here, you can have a richer decomposition than here. They have 5 instead of
But what's
3.
the symmetry? I mean, that is where I'm.
What do you mean symmetry?
The flavor symmetry.
well,
So
we-
how
we-
can you like?
We don't have to assume symmetry. U and D,
let it do this way.
U and D and S all have different masses.
Ah.
I don't have to assume they are
Okay.
symmetric.
No.
But you can have a combination.
Nevertheless.
Right. You don't have to, in other words, when we do experimental, you don't have to assume symmetry. Symmetry helps you in certain cases, but you don't have to. But in the renormalization, you take a mass-independent renormalization scheme, that the renormalization is at 0 mass, and everybody is the same.
Okay.
Okay, so that's why I said using this thing, then this is the linear equations. You can just resum this and give you this. It's exactly the same thing as I said. But only doing this, that's what we do in the lattice. It has it's a richer structure. And I was trying to convince experimentalists to be able to find out a way to do this, then you can compare directly with it.
So then there should
With
be
the
an observer.
lattice.
Yes. Yeah.
That's the point. I thought it was workshop is about. Anyway, so this is a disconnected searching results. As I said, 3 lattices, but we have to do the partial requenching results of each one. That's probably 5 passes, or about 15 points. This is the physical point here. Then these are 300 MeV. Then you extrapolate it with this functional form A squared and exponential forms to get a volume. And this is strange. But when you look at this thing here, we can hardly detect any order A squared. It's very small. Can really not. So this is overlap, as we said that if you look at other things, if you go very large at different actions, this is a very small scale. We have a fluctuation. It's very hard to do extra A squared extrapolated. Here is almost constant as far as A squared is concerned. The other dependence, this term just dominates, the n-pi squared dominates. For the connected assertion part, we also have the similar situations for the U quark and D quark, as I said, separately with various lattices, and you use the functional form to fit it. And it turns out the order is square dependence is also very. You can hardly see it with the overlap. Okay, now here's a table summarize some of the results that we have mentioned here. This is delta U, delta D connected, disconnected. Delta S, the total delta U, delta V means delta U plus delta U bar. Okay, and this is the difference, which is isovector GA. This is total speed. This is the results from Jeremy Green, which is 1 lattice with a relatively heavier power mass. And this is what Martha's results here with the one that I have only has a 1 and a 2 and 1 power mass, 1 lattice. We probably have new results. That's what we have. And this is what we have, as I said, based on 3 lattices, 5 to 6 valences on each of the three lattices with the power mass as small as 1/7. Okay, and as I said, we've done renormalization and normalization correctly. Okay. You can see that delta U, delta S, as you can see this point, which compared to, I don't know what is the latest results, what the burner has, but this is what we have. It's larger error bar. And this is turned out to be relatively small. Delta U turns out to be larger than what these results is. And delta D, more or less. But you can delta U minus delta D. You can see that we have a 1.254, 16, which is within 1 sigma of the 6 result. The best calculation, or best in terms of precision calculations, at least with this one, but we are only 1 sigma away. Okay, whereas these two are so small, and that was a little surprising that experimentalists, or not, the global fitting didn't constrain us to it. They had the results which is less than 1%. Why didn't you constrain us to the experimental?
We do.
You do?
Yeah. This
Okay,
is
I
only, I think what's good is there must be like a region from 10 to the minus 3 to 1. Because, for example, the 0.366 we have on the right, sigma is not our value for delta sigma, it's much smaller. Because we find like 0.25, something like that.
Oh,
so
okay.
this comes from low X, which we kind of control, but
we should probably talk to you. What's
this
the
would be only
proper way to quote it? This is, look at it.
this is only X bigger than 0.01.
Okay, but the thing is that delta sigma turns out about 1. 4 or 5. This is about less than 10%. Hopefully, we would like to have this. We have only 3 lattices. We have 5 or 6 lattices with several of them in the physical biomass, different volumes. Hopefully, eventually, we'll get it down by say 5%, 6%, 7%, and that's our goal. I think we are heading toward that direction. Okay, what are the systematic errors? Now let's go on. Oh, one thing I want to mention is the interplay between the sophisticated and topological charge in the anomalous water identity is something related to this disconnect distortion, and that's another example. You can see the U1 anomaly precisely. Okay, in the future, it will be even desirable to use the exponentially local operator, which has been devised by Peter Hasenfratz for overlap specifically. In that case, we can get rid of the normalization. That's exactly what we already implemented. That one. It's a little more complicated to calculate, but in that case, we don't have the normalization, only normalization. Now, where does this rest of the spin come from? The glue spin, orbital angular moment, and so on. I won't touch them here today. I don't have time to talk about them. The next issue is then the mass and momentum fraction. But before I do that, I should mention the decomposition of energy momentum tensor. And moment and angular moment from the I'm taking the Shandong's decomposition for this moment. In that case, these two are gauge. The glue and the quark are simplification invariant operators. And but then this can decompose the spin and the orbital, which is covariant derivatives. And this is just R cross the Poynting vector, and it cannot be further decomposed into the orbital and spin, unlike Jaffe-Manhart, which is a separate topic today. The way to calculate them is using the nuclear form factors. Okay, instead of directly calculating the R cross something which is a little hard on the experiment on lattice. You have a T1 and T2 form factor. Oops, somehow I missed a lot of indices here. I don't know what happened to the the same Mac. Anyway, you can interpolate. This is a USR. Okay, forget it. I use the T1 test.
Put in.
You should not ask for full test. You should ask register. Anyway, the same thing as I call that T1, T2 because following the F1 and F2 electromagnetic form factor, where here the T1 is 0, it's a momentum fraction, the other one is angular momentum fraction. For the F1, F2, this is the charge, this is the magnetic moment. So you have a sigma mu, this is a sigma mu without Q mu. So, okay? And this is Q mu, Q mu. Okay. Anyway, I'm missing all the indices. Okay. Anyway, so one can use these relations in the momentum from the momentum and angular momentum sum to normalize it. Before I do the renormalization, which is an important issue, but I should mention there is a normalization one to take care of, like this, just like this, the GA, is that you have a normalization for the momentum fraction and for the quark and the glue operator, but you have a two-sum rules. When the momentum sum up, I missed all the brackets here somehow. Anyway. It's a momentum fraction, okay? The momentum fraction should sum up to 1, angular momentum sum up to half. So the T1 and T1 sum up to 1, T1, T2 sum up to 0. So T1 and T2 should cancel. We have I don't know what. Okay, this is mixing. We have all the mixing coefficient, which is where I'll have another slide to show you what it looks like. Here is just the first one. Is we did this first in the decomposition in the quench bar expansion as a test. How things come out with the momentum, the angular momentum, summables, and so on. These are turn out to be fine. In that case, we get the quark spin to be 25%, which is not bad. But the glue turned out to be rather small. As I'll show you, our glue in the dynamic formula turns out to be larger, and the difference will attribute that to the orbital, right? Just differences of calculating, and a majority of that comes from the disconnect insertion. The connect insertion is very small because we do the cancels out. Many people have seen that. Okay.
If you compare this directly, so
sorry.
Work orbital and Q
you compared it here?
We did not compare it directly. I think Engelhardt did something calculation with, she has simulated and calculated.
Then how do you know this decomposition is connected in this way if you don't calculate it?
What it is, we calculated the total momentum of the quarks at the connected disconnected. We calculate the spin connected disconnected. That's how we get angular momentum. We only do subtraction. This is only from the subtraction of the angular momentum and spin. Where they did is actually, you didn't do the disconnected.
No,
you did only the connected
that's
part.
That's
You
not
do the
understand.
connected part and doing it directly across something. And show that the results are consistent from with the subtraction. We have not done that ourselves. Okay, before I show you the later results, at this moment with the disconnect insertion, as I said, you should calculate T1 and T2 to get a whole story. We have not done that yet, and that's complicated. We're in the process of doing that. We should have it, but but from the hint of the quench approximation is very small. T1 is a few percent. As Martha mentioned yesterday, they saw it to be 0. I mean, that's small. So this moment we'll assume that T2 is 0. In that case, the momentum fraction is the same as angular momentum fraction of 2 factors. Okay. So assuming that, let's just show you later, the momentum fraction of the blue is like 48%. So later. And the U, delta U is 85% here. And delta D is negative 41. And delta S is negative 4 or so. That gives you a total spin to be 40%. And this is blue is 48% momentum fraction. We'll take that to the angular momentum fraction. Then it gives you 12% of this thing. But I think.
And the scale? The scale?
2G. And I think this one is a little larger. And then, as I said, I speculated around this. The angular momentum is such that will make this a little smaller, and that will probably get up to 20%. So 13 to 20% that's what we estimate.
So is it always the case that the angular momentum fraction should be the angular momentum contribution? I mean,
no. The momentum and angular.
Right.
There's a difference. Remember, the momentum is T1. Angular momentum is 0. At this moment, I'm assuming T2 is 0. At this moment.
Oh, okay. That's
at this
okay.
moment,
Okay.
This is a little more involved. We are in the process. I don't have to. That's why I'm preliminary. We don't have to. I'm not going to show this. My suspicion that will be a little smaller.
Okay.
Like 6%, 42.
But so right now in yours and Martha's calculations, I should not be surprised that the numbers are the same for the two quantities.
Because the numbers are very different, but
no. The numbers.
But the approximation is the same, right? Yes.
And phenomenologically, we shouldn't be so surprised because the up and down anomalous magnetic moments are about equal and opposite, which suggests that the gravito-magnetic moment sum rule, which says the total is 0, is almost saturating the up and down course. That doesn't leave much room for the glue, which means if you set it equal to 0, the contribution from the glue to the anomalous gravity-magnetic moment, then the momentum fraction is equal to
the thing is this, if I do it correctly here, the sum is 0. In fact, what we found, this is like 0.06 or so in the quench approximation, the large error bar. This are to be negative, this is positive, they cancel. In our calculation. So therefore, our realization, this is mobilization is like 1.05 for the quench. Technical, we don't know yet. We're still working on it. But there should be some experiment, some difference. I hope it's not 0. Anyway. Okay, let's go to the mass. The puzzle of the mass, of course, is always that, of course, the Higgs gives only a very small quantum masses, and that you add up to U1D give you only 1% of the total mass. That's where the rest of the mass come from. Now, to do that, we have to do the the quark and glue decomposition. Again, using energy moment tensor, you have the momentum mu is PBP mu here, n squared. Then there's another relation to the trace anomaly, okay, which gives you the glue part and the quark part of the anomaly. And then we can separate out the traceless part and the trace part. And traceless part, of course, is related to the momentum fraction, as we know, which has a scale dependence, which is sum up to 1 for the quark group. And for the trace part, which is medium squared, which is minus n for the rest mass. So we can decompose this according to Sheldon. We can decompose it this way. Once the masses can be written as a T44, the Hamiltonian, which has the H quark, H gluon, and a quarter of the anomaly. Well, which is H quark is D4 gamma 4, and the mass term. The anomaly is B square E square minus E square. This is Euclidean in the viscosity is B square plus E square, and then this is an anomaly term. This is the glue field energies. Okay, those are Kashmir effects. But using equation of motion, you can find that this can be rewritten as the energy of the quark, so the values, and mass condensate, mass times condensate, and the glue energy and the quarter of the anomaly. Okay. First, we want to calculate nuclear mass. Okay. Now we add another lattice now, 48 cubed. Physical biomass, 5.5 firm. Very well. Okay. And these are 4 lattices that we have. And these are the masses that are calculated. You can see they come up very little, 24 and 32. 24 and 30. This is triangles here. You can see they are near the unitary point. You can hardly see any difference. There's no order, even though they differ by 30% amount of spacing. So you can hardly see any square. We just used some mixed action because we used overlap on the wall configuration. There's in principle is mixed action, but the low energy parameter which specifies this mixing for dollar mix is very small. An order of magnitude smaller than the other mixed action, like cooler all staggered or wall staggered. It's order of magnitude small, which is negligible. We take that into account, but couldn't fit it. It's not working. Turns out if you just let it fit with the G8 and G1 as free parameter, you get 960 and you get a power limit and a physical point. But if you just fix this to the experimental value, then you get a closer result, 931. But the chi-square is large. So the next step, we're going to have to throw in more lattices and with the more points at the physical point to see whether we can control that situation. Understand speaking. That's about the best we can do for small, or anybody can do. Now, the non-perturbative renormalization, which is going to be very important. Non-perturbative renormalization is very complicated. You have a quark and mix with a glue. And this factor in the glue matrix element, the glue operator in the glue propagator is very, very, very noisy. Okay, you have to do something in order to see that. The one way to do it is the following, using the glue renormalization. You have a glue operator here, and you have A fields and 2 A fields for the glue propagator. And it's very noisy because if you consider glue ball a noisy calculation, it has only 2 noisy gauge fluctuations. Here we have 3. There's a glue operator, 3 of them. It's just impossible to see, as we can show you later. So the one we did is apply the cedar, we call it classical decomposition, error reduction. You cut this point, you cut that point. Because these can be far away. You can cut it at R1 and cut it at R2. These 2 points you can limit and try to restrict it. Okay, let me show you one of the renormalization constants for the traceless one. These are our error bars for the calculations. And you're supposed to extrapolate this A squared T squared to 0 to get an RI region. Get rid of the finite A squared T squared errors, which eventually we get what these are. The error bars hard. But to test this, I won't have much time. What we did is one thing to test this, we used a crunch approximation with 70,000 configurations, which we can do. And we use only 1% of that in doing this cutting and doing the fitting. You find that they can be in agreement if you do the cutting. Otherwise, you get this result. Okay? And so this one is dynamical fermion with a 21,000 configuration. We used, again, a 10% of this thing, and then you can see that that's with certain range, they can be made in agreement with the higher distance. Okay? Another thing we check is the following. Now, what operators you use, and what smearing. There's different operators which can define the energy moment tensor can be from the plaquette or from the sort of Clover term, and they give you different results. Okay, this is the same because this is the trace part and off-diagonal part cannot be the same, so that's the same thing. But you can have very different results. You know, they differ by a factor of 5 for the renormalization. It's no argument. However, when you copy the matrix element you calculate with this operator also differ by a factor of 5. When you put all this together, you multiply this all together, you get almost the answer. Yeah, that's okay. This is predominant mixing with the quark. Turns out that we have a paper now with non-predominant mixing with the quark, which turns out to be large. Okay. So, all in all, let me show you what the quark is. This is the pi squared. This is the d. This is a u in the d momentum fraction. And then you have 32 different lattices, which we put them extrapolated. One is this is probably u. This is a d. And then we have this is the glue, and this is the strange. Okay. Now the glue, as you can see, that with error bars tolerable. Well, the matrix element is much larger than the other calculations. And of course, at the end of the day, we have to know. The thing is that, as I said, we should normalize it with the moment and the angular momentum sum, but we don't have the angular momentum sum at the moment. It's just the momentum sum rule. Use the one normalization constant to define that to be 1. It has to be satisfied. But of course, in principle, you can say, well, I don't have to care because this is a finite renormalization. I can let last go to continuum limit. The continuum limit frequently is very, very far. The better way, people do vector charge, axial vector charge, finite reality. You use the order identity or whatever summary you can have, make it to be satisfied, and then extrapolate it much better. And that's what it is. Okay, you can look at the normalization constant, which turned out to be 0.8 or so. You can see that this is the lattice between 24 and 32, the relative same quark mass. This is about 0.114 Fermi, this is 0.85 Fermi. So it's moving in the direction of going it's smaller than error bars cannot tell. So this is normalization factor that we apply to it. You can see 20% or so. Okay. Now the end shot is the following. You have the momentum fraction, 31%. D is 16%. S is 5%. Compared to what a CP10 is. Well, I have not forget this is a U and then D and S. They have a U bar and D bar, which is separate. This is total. They're different by a few percent here. But the U is about 30-some%. D is about 16 or so on. And strange is, which is hard to say, and blue is about 42% with the 40%.
Completely. Previously showed the results for T1 for gluons and blocks in context of ensemble.
This is a momentum.
Yeah, but it's the same, right?
This moment assumed to be the same. But as I said, you should not trust the other plot, which is the kind of eye. Here is what we really get for the momentum fraction. We have not the total momentum fraction yet until we do the T2. The earlier results were assuming T2 is 0. Okay. But here is forget about previous. This is a momentum fraction. 28%, so that compares. Okay. Now, for the proton mass decomposition, of course, remember the energy moment, the energy of the glue and so on are related to the momentum fraction. So you can see this is a quarter, 23% is a quarter of the anomaly, trace anomaly. Mass term give you 5%. This is from earlier calculation with the 5 lattices. And the 32 is coming from the quark energy, and this is the glue field energy.
So the quarter of the trace anomaly and the quark mass term, are up to exactly one quarter?
No, this one is to have a glue and quark anomaly term. It's a quarter. Put it this way.
Some of these two is exactly one.
Put this way. Okay, if I do that, this is another two summary. The thing is, you have if you use the momentum, the mass is just this plus the total of the anomaly. So total is 91% is is an anomaly. Only 9% of this is from the part mass contributions. But this is one way of sliding them, slicing this way. Another, the one I show you is another way of slicing. I should have a 2 pie chart. We do this pie chart, part mass is 9%. The rest is all of them are not. And this one will just take a quarter of this thing here, and the rest, the other 2 quarters, the other 3 quarters divided into the part with a scale dependence. Otherwise, these two don't have scale dependence.
So you've done all these matrix elements at the for the forward limit. So
yes.
think about GTMD,
yes.
CPDs. Can you go forward with your the external momenta?
Yeah, you can. We haven't done that. Okay, yeah. You can do that. Yeah. You can do that with a momentum transfer and so on. That'll give you and this momentum form factor and so on. Okay, so here is a plot where we show this various contributions as a function of the part mass of the part mass. You can see other than the mass condensate equations, all the rest are fairly stable and constant up to about 480 part mass. We know that when it comes to the chart, everything's dominated by the chart mass. But at this moment, all the others seems to be, not that. Okay. Now here is something which probably people will pay attention to, is that look at U minus. Most people got this 20% higher, 1.8, 0.18, 0.2, and so on, and the global fitting is about 0.6 or so. Okay, and this now we got this thing down here because of the normalization. But in order to include the normalization factor, you need to calculate connect insertion, as people do. You calculate the disconnect insertion and the glue all together to get just U minus. Because besides renormalization, people hope, oh, well, this doesn't mix with the glue, it doesn't mix with the disconnect insertion. Fine, you have to make sure the whole summer will be satisfied. Once you have a summer satisfied, this comes down right away. Okay, so that is our solution to a value which have these people, it's on a white paper, people have been struggling for many years, and that's our simple solution. Okay, which is hoping that together with evolution, factorization, predictive QCD, lattice QCD, with a small enough system and systematic errors. So assuming that everybody's happy and different groups have come to the same conclusions, and that hopefully will be helpful. Either compare with experiments directly, or hopefully can help experiments better understand physics and a better fit.
Okay, thank you very much. Some more questions?
It's slightly off topic because you said you weren't going to talk about it, but what's the latest on the new speed?
Not much progress yet. We're still hoping. We rely on EBOR. Oh, I should say that this talk is supposed to begin about EBOR. Yeah, we just went back to China to pick up an academic position there. It's not enough time to do visa. But he's the one who's doing that, and you can see when we mentioned that he's doing all this positive. Yeah. He has only 2 hands.
No, yeah.
But we are working on. It's not easy to implement that. It's different gauges.
Yeah. You are using this K, the current K for that, or what do you?
No. We used whatever Tata and Shandong's margin. You cross A, but A has to be.
Yeah.
Earlier you use Coulomb gauge, but should that's turn out the one loop. Large momentum effect theory is very ineffective. It's huge, in fact, it's 5 or something. So it's totally not usable. So we have to look for other gauges where it doesn't have this one. That's the thing that we are searching for. Otherwise, the results, the lattice calculation is fine, but it's just pinned down by the large momentum effect theory. Yes?
I had another question. What about the third form factor?
The D term is all. Yeah, when we calculate the T2, well, we'll give a crack to see how we can get extract. It's very hard to extract it. It's very noisy. especially the blue part. Yeah. Oh, sorry.
When you compute the trace anomaly.
It's a good question. We avoided here. Right?
Yeah,
We will totally
just
avoid.
block it.
But then you can calculate the G-square term, which is fine, and we know how to do this lattice calculation. But you have to calculate beta function to make sure that is thing here, right? And you make sure that everything's good. Utilization could be there. That's
That
not
has been
easy.
done for lattice.
I know you're working on it. People, I think Martha wants to do it probably. She probably has a better answer. But you want to make sure that everything is representing group invariant, and it's not easy. And one thing again is going back to Suzuki.
Yeah, this.
Grading flow, and so
gradient.
it is on paper it's very nice, very beautiful. But then you have the 5 operator. We have only one operator. I mean, the 5 operator is a lot of mixing and doing it in a continuum. It's possible, but yeah,
Can I
sorry,
ask
sorry.
about the nucleon sigma terms? So
Yeah.
right now you're actually fitting the nucleon mass, but there have been some discrepancy between fitting the nucleon mass and the direct calculation. And
Right.
for overlap, it's really
We have,
perfect to do the
We also
It's coming
we did the slope. We did a slope
Right.
one. It turns out 52 plus 8.
Right.
So it's consistent with the direct calculation.
right.
But
But there have been people doing both methods. They don't agree. Like Regensburg, for example, their direct calculation and their fitting nucleon mass.
how do you fit nuclear mass with a term which does not count the big power symmetry? I have this question about BMW. How can you fit in the Feynman-Hellman theorem, right? Feynman-Hellman
Right.
theorem is not, you cannot use it. Look, you calculate the connect insertion and disconnect insertion, right? Now the beauty of overlap or power from is m times psi bar as renormalization could be there. Take it, cancel. With the Clover, there's large mixing of the UD flavor and S flavor.
Yeah.
Right? Unless you go to the continuum first before you do, then you do just using the derivatives, not going to do it. You have to do it connect and disconnect. Make sure that you do the renormalization, taking into account there's a flavor mixing. I don't know how much people have done, but overlap, you don't have to worry about any of this.
Right. That makes you calculate the scalar matrix a little easier than other people.
Renormalization is much easier.
Yeah.
There's no renormalization. It's
Right.
renormalization could be there.
Right.
But for Clover, it's very, very different.
Sure. But
Yeah.
do you have
Do what?
the scalar?
Yeah, this has been published 2 years ago.
Okay.
40 something, I mean, strangeness and UD.
You do, yeah.
Yeah.
They are consistent with their nucleons.
Consistent with what?
With the story for nucleons.
As I said, that we get, how much we get? 44 times 44 something. They did the error bar touch. Doing the slope is a little larger, 52 and 8. The other one is 44 and 6 or 7. So it's an error bar do touch. I mean, it's overlap.
Okay,
Okay.
there's no more questions, and I suggest we do coffee break until 11, and then come back after that.
Yeah, I can use some